The fascinating journey of cement production and the subsequent manufacturing of concrete is an intriguing exploration that originates from the extraction of crucial raw materials and evolves into the ultimate building material, forming the backbone of countless structures worldwide. In this extensive exploration, we take the time to delve into the various stages of the cement and concrete production process. We'll show you where the renowned Portland cement comes from today and how it originated. We take you on the journey of cement production. Let's begin. The initiation of this complex process involves the extraction of essential raw materials, namely limestone and clay. These materials are often obtained from quarries, employing various methods ranging from controlled explosions to the use of heavy equipment. The ultimate goal is to extract these raw materials from the Earth's crust. Once extracted, the raw materials are transported to a crusher, where they are thoroughly crushed into smaller pieces. The essential follow-up to this crushing process is the careful mixing of crushed limestone and clay in the right proportions, resulting in a raw material. This raw material then undergoes refinement in a mill, a rotating cylinder that grinds the raw materials into a fine powder. This crucial milling process not only contributes to the effectiveness of subsequent chemical reactions, but also ensures a uniform composition of the raw materials. The fine powder of the raw material is then subjected to heat in a preheated tower. Hot gases from the furnace are used to increase the temperature, leading to partial calcination. This phase involves the decomposition of carbonates in the limestone, resulting in the formation of calcium oxide, lime. The preheated and partially calcined raw material is then directed to a rotary kiln, an impressive cylindrical structure where the temperature can reach up to 1450 degrees Celsius. In this kiln, the raw materials undergo a series of complex chemical reactions and sintering, resulting in the formation of small marble-sized clumps, also known as clinker. This clinker, consisting of calcium silicates, aluminates, and ferrites, is discharged from the kiln and cooled in a specialized clinker cooler. The cooling process is crucial to maintain the quality of the clinker and prevent unwanted crystal structures. After cooling, the clinker is ground with the addition of gypsum and other additives such as stainless steel, glass, and carbon in cement mills. The addition of gypsum regulates the setting time of the cement. With the cement now ready for transport to concrete plants, it is necessary to ensure production quality. Laboratories in cement plants conduct frequent chemical and physical tests at each step of the manufacturing process. They also analyze the end product to meet stringent industrial specifications and standards. Now that the cement is ready, we shift our focus to obtaining the aggregate, which can make up to 75% of the concrete volume. The aggregate, composed of gravel and sand, undergoes careful selection and mixing. A well-graded aggregate, with a balanced mix of coarse and fine particles, reduces the need for cement and contributes to the cost efficiency of the entire process. Let's also consider the crucial role of admixtures in concrete manufacturing. These chemical additives offer various benefits, such as improving workability with plasticizers, accelerating or slowing the setting time with accelerators or retarders, and reinforcing concrete with stainless steel, glass, or carbon fibers. With all raw materials in place, the concrete production process can finally commence. The concrete mix design, a specialized discipline, comes into play to determine the correct proportions of cement, aggregate, admixtures, and water based on the desired tensile strength. Building codes further specify these proportions depending on the type of construction. The mixing process itself, once manually performed on concrete slabs, is now automated using concrete mixers. This not only speeds up the process, but also ensures that cement particles are evenly distributed over the aggregate. Water is gradually added during mixing, leading to the formation of cement paste. The hydration process, generating heat, continues until the concrete achieves a uniform consistency. After the mixing process, the concrete is transported and placed at the final location. Whether poured directly into formwork molds or using specialized equipment such as pumps or conveyors, it is essential to avoid segregation. Compaction, using vibrating equipment or mechanical means, follows to eliminate voids or air pockets and ensure the strength of the concrete. Curing is the next critical step, maintaining sufficient moisture and temperature conditions to allow the cement to hydrate and gain strength. This process can take several days to weeks, depending on the type of concrete and the desired strength. Various finishing techniques can then be applied to achieve the desired surface texture and appearance. Thanks to the versatility of cement, it has become the most widely used building material in the world. In the United States alone, over $4 billion worth of hydraulic cement is produced annually, used in $20 billion worth of concrete constructions. Globally, the concrete industry is estimated at over $600 billion, highlighting the immense impact of this essential building material. As we delve deeper into this extensive process of cement production and concrete manufacturing, it is important to acknowledge that every detail, from raw material extraction to concrete placement, is meticulously managed to ensure the highest quality and durability. This careful approach is essential, given the ubiquity of concrete in modern constructions, ranging from bridges and skyscrapers to residential homes and infrastructure projects. As we explore the sublime ballet of chemical reactions and physical transformations taking place in each phase of this process, we witness the art and science behind seemingly mundane concrete structures. Concrete, in all its simplicity, is the result of an ingenious interplay of raw materials, technological processes, and human expertise, each element carefully balanced to create a material that is both strong and versatile. In this extensive exploration of the world of cement and concrete, we have not only emphasized the technical aspects of the production process, but also the widespread impact on contemporary society. The significance of concrete extends beyond the construction sector. It reaches into the economy, sustainability, and the daily lives of millions of people worldwide. As we complete this journey through the concrete production process, we realize that the apparent simplicity of concrete conceals a deep and intriguing complexity. It is not just a building material, but a symbol of progress, sustainability, and the human drive to create structures that can withstand the test of time. The history of cement has ancient origins, dating back to ancient Egypt, where a mixture of limestone, clay, and water was used for structures such as pyramids. The Romans added volcanic ash to improve it. After the Roman era, the use of cement declined until the 18th century. In 1824, Joseph Aspdin discovered modern Portland cement in England. This cement, named after the Isle of Portland, is still widely used in construction. Since then, various types of cement have been developed. Cement is now a crucial building material globally, used in everything from homes to bridges and roads, having an indelible impact on how we build, live, and progress. If you're interested in learning more about production processes, from raw materials to end products, watch our other videos and subscribe, like this video, and hit the notification bell to stay tuned. Thanks for watching.